So section 1.2 is about the geometry of linear equations. So what is a system of linear equations? So linear equation, I mean the system of linear equation, not a single equation, but well, collection of linear equations. So first, let me introduce the system of linear equations. So I will begin from a very silly example. Suppose that you have encountered such a system of linear equations. 연립일차 방정식. So I guess you guys have done this. I think you're pretty good solving this question. Well, better than mine, better than me. And well, if I spend reasonable time and effort solving the equation, then it turns out the solution of the system is 2x equals 2, y equals 3. So this is the solution. So everyone knows how to solve it. But well, in this lecture, but solving the system of linear equation, well, looks not a big deal. But actually, well, this is my personal viewpoint. But so linear system, if you can solve the linear system, then you can actually solve everything. So not everything. So there are many nonlinear problems that you might encounter in your career. But well, most likely you cannot solve any single nonlinear system. So what you're supposed to do is try to convert for given any nonlinear system of equations. Then you should be converting that nonlinear problem into system of linear equations, and you solve it. So that means if you can solve linear equations, then you can solve almost all mathematical questions that you can encounter. And finding a solution of the system of differential equations, especially in this case, I have 2 unknowns and 2 equations. And the Professor Strang, he tries to introduce 2 different viewpoints, especially 2 different geometric viewpoints regarding the systems of linear equations. So first viewpoint, so he's saying a low picture. What is the low picture of a system of linear equation? Well, which is very easy. So I have 2 equations, and well, I should like call each of these equations a law. This is first law, and second law, and every law can be translated to a line, right? So well, 2x minus y equals 1. So I can try to draw a line whose slope is 2 and y-intercept -1. So this is going to be my 2x minus 1 equals 1. And this one can be translated to another line whose slope is -1 and y-intercept 5. And in this case, the one and only intersection point of these 2 lines should be the solution, right? So, well, so I would like to say something about each of these equations because, well, I have this plane is x and y plane. So, well, so I have 2 free variables, x and y. Well, okay, if you like, then you can call it 2 unknowns. Well, I have 2 free variables, x and y, and Well, I have one equation means that I am restricting one constraint to these two free variables, right? So, well, be having two free variables means that, well, everything is two-dimensional, but, well, after I impose one constraint, then that means then the set of all x and y satisfying this one constraint should be 2 minus 1 dimensional geometric object, which is a line, right? Right? So this is why we are having a 2 minus 1 dimensional geometric object. well, 어렵게 얘기하죠. Well, 2 minus 1 geometric object, which is a line corresponding to each of these rows. So this is what I mean by row picture of the system of equations. Okay, good. So, well, let me change my example a little bit more complicated. This time, no. Well, what I have here is a system of linear equations with which consists of 3 unknowns and 3 equations. Well, and let me try to draw a row picture of this problem. Well, here I have 3 unknown, 3 free variables. So without any constraints, so everything should be in 3 dimensions. But this one equation, in other words, this one constraint is gonna give us one constraint to 3 free variables. So having one constraint means that I am losing 1 degree of freedom. So that means this is what? This is a 3 minus 1, which is 2-dimensional geometric object, which is a plane, right? So this is a plane, and this is another plane. So this is another plane. So I have 3 planes in 3-dimensional spaces, right? So, so even if so I will not try to spend too much time drawing each of these 3 planes, but well, you can imagine. So you can try to imagine the picture here. So so in this case, if you solve the question, then you're going to get 1 and 1 and 2. So that means if you have 3 planes, 3 of these planes, where if you have 3 of these planes, then if you try to find a one single intersection, well, no. So then the intersection of these 3 planes should be exactly 1 point, which is 1 and 1 and 2. So this is what I mean by the row picture of differential system of equations. So generally speaking, suppose that you have a linear system of linear equation, equations of n unknowns. And equations. So then, according to our row picture, then a solution of this system is going to be the intersection of n minus 1 dimensional geometric object, which I will call the n minus 1 dimensional hyperplane. So of n minus 1 dimensional hyperplanes. And well, if you have n unknowns and n equations then most likely you're going to get exactly precisely one solution, right? That means, well, that means most likely in this case, the common intersection point of all these n minus 1 hyperplanes is going to be precisely one point. Yeah, that's that. The intersection of these n minus 1 dimensional hyperplanes, a 0-dimensional space, which is a point, right? Well, you can think you can try to understand in this way. So, well, introducing one constraint means you're losing 1 degree of freedom. So I have n equations. That means n constraints. So after you're losing n degrees of freedoms, then you're going to have 0 degrees of freedom, which is a 0-dimensional space. All right. So this is about the low picture. Nothing very special, right? Now, I'm going to introduce another picture, which will be called a column picture. And in order to introduce the column picture, then I really have to say something about the vectors and vector spaces. So, well, what is a vector space? Well, if you have attended any multivariable calculus course, then you must be familiar with this notation, Rn. So what is Rn? So this is n-dimensional Euclidean space, which consists of n tuples of real numbers. This is Rn. And typically, a element in this space, which I will write down as a scripted V, or the boldface V. So if I put one additional line over here, then you should consider it as a member of this one. And a typical element in vector space Rn looks like this. And each of these numbers, here, so this is not boldface letter. So this is just a regular letter. And this is a number. And this guy consists of these n numbers. And each of these numbers I will call a component. Well, suppose that I have chosen 2 random elements out of Rn, and in this case, I can introduce 2 operations on these V and W. So first one is the addition or vector addition. So what is the vector addition? Well, which is very easy. Defined as nothing but a component-wise addition. So this is the vector addition. And the second operation is a scalar multiplication. So this is again easy. Nothing but every component is multiplied by some constant. Well, C. C is here. C, this letter C is not in boldface, so that means this is not an element of this guy, but this is nothing but just real number. C is a real number. So Well, I'm gonna call this operation as a scalar multiplication. Well, I'm using, so maybe some of you are not that familiar with the terminology of the scalar. The scalar is nothing but just some random number. But I call it a scalar because just to emphasize this is not an element of Rn. So this is two basic operations in this space. And then between the vector addition and scalar multiplication, I have these 9 very elementary operations. Elementary properties. What are these? So 0. This is very special element in this space. So that consists of every component of this guy is nothing but 0. And 2. The order of vector addition does not matter. So if you are supposed to suppose that you want to add 3 vectors, then this means you're always free to add this guy first and this guy later, and these 2 guys first and this guy later. The result is the same. And u plus v is v plus u. So therefore, the order of vector addition also doesn't matter. And well, the identity element exists. So this is this one. This is the identity element of the vector addition. And number 5, well, the inverse of vector addition also exists, which is what? The -1 scalar multiplication of -1 to the original vector is going to be the inverse element of the vector addition. Also, for the scalar multiplication, AB times of V, AB scalar multiplied by V is the same as this. And well, scalar multiplication by 1 is always itself. And there is also something like the law of distribution between the vector addition and scalar multiplication, which has 2 versions, this and that. Okay, so these are 9 elementary properties that you can expect from the vector addition and scalar multiplication, right? Easy. Okay, now I am going to give it a name. So what name? So, and actually, as a matter of fact, these 9 properties is a characterizing properties of so-called the vector space and vectors. So I think this is the right time to define our definition of the vector space and vectors. Well, suppose that you have a set, some random set. So I have no idea what it is. But also suppose that this set V happens to have 2 operations. With addition and scalar multiplication. If addition of two elements in V and scalar multiplication satisfies the all these properties from 1 to 9, then we say the V is a vector space over real numbers. So this is so these 9 properties defines what vector space is. And element of V is called a vector. So these two guys, the vector space and vector is going to be our protagonist of this this semester, the vectors and vector space. So let me try to imagine. So what are the examples of the vector space over R? So maybe I can think of, this is the most important example, what vector space Rn, which is n-dimensional Euclidean space, is a clearly vector space. And what else? Maybe a set of all real coefficient polynomials of degree less than or equals to n. Is that a vector space? Yeah, there should be a vector space. Well, maybe a set of all real coefficient polynomials, that is also going to be a vector space. And what do I have? Like, well, what about this collection of all continuous functions from defined on the interval from 0 to 1? That is also going to be a vector space, right? So there are many vector spaces. Really, like, well, if I want to exaggerate a little bit, then everything that you can find in this real world can be interpreted as a mathematician should be a vector space. So everything is a vector. One more thing. So, well, in this case, I am in this definition, I am choosing my scalar from the set of all real numbers. But well, there's no need to stick to the set of all real numbers. Well, maybe you can try to choose your number, not from the real number, but from the complex numbers. In that case, we say that is a vector space over, not over real numbers, but vector space over complex numbers. Okay. So if the scalar is a complex number, the V is a vector space over complex numbers. So in this course, we are mainly interested in, even though I have mentioned many different vector spaces, but well, in this course, we are mainly interested in the Rn and Cn. Sometimes, from time to time, I will be mentioning the Cn. So the Cn is what? So this is collection of n tuple of complex numbers. But we will be mostly working on the set or n-dimensional Euclidean space here. So this is our main object of interest. All right, and let me try to visualize the addition and vector addition and scalar multiplication. So how do we visualize a vector? So easy. Well, the easiest and the popular way to visualize any vector from n-dimensional Euclidean space is a pointed arrow, right? So if I suppose that I have chosen this vector out of Rn, then you can visualize this vector by a arrow which is starting from the origin and ending at that point, v1, v2, vn. So that is how we usually describe a vector. So this is, well, shortly speaking, so vector is an arrow with a direction and the magnitude. So magnitude, in other words, the length. So keep this one in mind, and I'm going to visualize the vector addition. Just like that. Suppose that I want to compute 1, 2 at vector addition with 3, 1. And the answer is, well, easy, 4, 3. So how do we visualize this? So this 1, 2, this vector should be drawn like this. So, well, this is the endpoint of this vector. And the coordinate of this guy, this endpoint is going to be x coordinate is 1 and y coordinate is 2. And, well, if I want to then visualizing this one, I will have a this vector, right? 3, 1. So this is my two vectors. And if I add these two, then I have this one, 4, 3, which is this. So how do we draw this? How do we draw this vector? So this is, well, in order to get the endpoint of this last vector, then what you're supposed to do is, starting from this endpoint, I go to 3 units to the left, to the right, sorry, and 1 unit up, right? So in other words, just here, I'm just parallel translating this guy to here. Or you can try to parallel translate this guy to here. So, what I have here is a parallelogram. So 평행사변형. So 평행사변형. So if you have two vectors, then the last vector, endpoint of the last vector, the endpoint of this resulting vector is nothing but the last vertex of this parallelogram of these vertices. Okay. So this is what we call a parallelogram node. Well, and scalar multiplication is also easy. Suppose that I have some random vector v, and I have a random vector v, and scalar multiplication of this vector by number c is nothing but stretching this vector by factor of c. Okay. So this is c times v. Well, what if my c is not positive but negative number? Then in that case, the direction of, well, oops, sorry. In this case, the direction of this arrow should be reversed, just like this. So this is minus of V, should be something like that. Okay, so let me try to visualize not vector addition, but vector subtraction. Well, hold on. So you have never mentioned vector subtraction. Vector subtraction is nothing but V plus minus 1 times of W. So here, vector subtraction, I mean by this vector addition. So let me try to visualize this. If I have vector, if this is my vector V, and if this is my vector W, no, this. Then, well, in order to do this, then first of all, I will need to scalar multiplication of scalar multiple this guy by -1, so which is this, right? This is minus W. And now I will need to add this vector by -1 of this guy, right? And according to my parallelogram law, so the resulting vector would be something more like sorry, my picture is not good, but well. So this one, this is gonna be my V minus W, right? So this is the vector subtraction. This is the visualization of vector subtraction. So if you look at some other textbook, other linear algebra textbook, then sometimes from time to time, the author of that textbook sometimes mentions the vector subtraction is nothing but drawing a arrow from this second vector to the first vector. If you connect these two and try to parallel translate so that the resulting vector starting from the origin, then this is how you get these vectors. This is how you get the vector subtraction. So, well, this is that. Okay, good. So I have spent a reasonable time on explaining vector addition and multiplication. Okay. Now, suppose that I have some vector space over R. And I have chosen K vectors, V1, V2, da, da, da. Suppose that I have chosen K vectors from the vector space V. Now, I want to introduce the concept of the linear combination. A linear combination of these K vectors is another vector that belongs to vector space B, vector, which is so this is what I mean by the linear combination. In Korean, 선형결합. So what is linear combination? Well, although this terminology sounds a little bit scary, but well, again, this is very easy. So what is this? But once you have chosen these K random vectors from the vector space B and try to scalar multiple each of these guys and add it all together. So this is, well, just a linear combination. Easy, right? So this is the linear combination. And Well, again, I have chosen k vectors from V. Now I want to define the word span. What is a span of these k vectors? So this is this. Aha. Oh, well, I have used a set builder notation, and this one on the left. So this is what? This is nothing but a linear combination of these vectors, right? So therefore, span of these vectors means nothing but collection of all linear combinations of v12 vk. So just try to imagine every possible linear combinations that you can obtain out of these k vectors. And collection of all these vectors is called what we call the span of these vectors. Well, so this is a subset. Also usually, so therefore this is a subset of vector space B. Okay. Well, here I have used so I have introduced, even if I have introduced the span of k vectors, but sometimes from time to time, I'm going to say, well, span of some random subset of vector space B. So in that case, so that means what? So even if the random subset of V may not be a finite set, but a span of that random subset is nothing but collection of all possible linear combinations that can be obtained by vectors in that random subset. So this is, well, so therefore, span of some random subset of vector space B is also possible. So we'll go back to that later. Oh, anyway, so this is span. So okay. Let us consider, so let me visualize the notion of the span. Well, oops. I suppose that I have these two vectors, U and V, which is two-dimensional. So everything, so ambient space is a two-dimensional Euclidean space. In this case, what is span of U? Well, span of a single vector. So what is a linear combination of a single vector? Well, that is nothing but some collection of scalar multiplication of vector U, right? So therefore, as long as my vector U is a zero vector, as long as my vector U is not a zero vector, then span of U should be visualized as a straight line stretching to this infinity to that infinity and passing through the origin and parallel to vector U, right? So this is how you visualize span of one vector. So I'm going to call it a line. Well, very convenient word, generated by vector U. So this is how I visualize the span of a single vector. Now, what about span of two vectors? Sorry, not like this. This is slightly trickier than before, but span of two vectors. So this is, well, a set of all linear combinations of vector U and V. So, well, according to the parallelogram law, so this vector U plus V also must be a member of this guy. And 2 times v plus u should be also a member of this guy, right? And like 1 million times negative, like 1 trillion, 1 bazillion of this vector also must be the member of this set, right? And if you imagine collection of all these linear combinations of vector u and v, then I think you can easily be convinced that the resulting vector, resulting span uv is precisely the same as the two-dimensional vector space, right? Just try to stretch, just play with these two vectors. Try to stretch this one u a little bit and v another little bit. Then if you add together by using the parallelogram law, then every point in this space can be achieved by written as a linear combinations of these two. So this is, well, this is a two-dimensional space generated by u and v, so which is, in other words, the entire ambient space R2. Okay? Okay, good. All right. Okay. Well, well, let me increase my dimension by 1. Well, my picture is not that great, but this is my u. This is my v, and say this is my w. I have these 3 vectors, and well, in this case, the span of u is, this is again a line generated by a single vector. So this is what? So visualizing this, so this is a line which is parallel to vector u and stretching to this infinity to that infinity and passing through the origin, right? So this is the, so you know the line. So I don't need to draw it, right? Okay. A line generated by vector u okay. Now what? Oh, sorry. My handwriting is getting messier. This is, well, this is u and this is v. Sorry. What about the span of u and v? Well, this time, so this is nothing but collection of all linear combinations of vector u and v. And again, just try to play with these two vectors. Let's stretch vector u a little bit and stretch vector v another little bit, and you add them by using the parallelogram law, then what you have would be a two-dimensional plane which is passing through the origin, and that contains the vector u and v at the same time. So that is going to be the resulting geometric picture of span u and v. A two-dimensional space generated by vector u and v. Well, even if I am using very convenient word generated, but generated means that this plane must contain the vector u and v and passing through the origin. Okay. All right. Lastly, now we turn to the span of these 3 vectors, u, v, and w. So, well, my picture is not that crystal clear, but you can consider 2 scenarios. Suppose that my last vector, w, is not contained in two-dimensional plane generated by U and V. In that case, span of these three vectors would be the entire three-dimensional Euclidean space. Okay. Yeah, some of you nodded. Thank you. But in other words, but if another scenario is, suppose that my last vector W is completely contained in the two-dimensional vector space generated by U and V. In that case, this may not be R3. In that case, this is exactly the precise. Well, even if I have used one additional vector W, in that case, this guy would be exactly the same as that guy. Okay. Well, but however, the second scenario is not very likely, right? So, so therefore, most likely, so almost always, span of these three vectors should form an entire three-dimensional space. So I will say this is a three-dimensional space generated by U, V, and W. So which is nothing but R3. All right. So so now we know how to visualize the vectors and how to visualize the span of some couple of vectors. Now I am ready to introduce the second picture. So the first picture was the low picture. So, well, we can consider a given system of linear equations as a low picture. Now I am ready to introduce the second picture, which is the column picture. So what is the column picture? From now on, even if we write a vector in Rn like this in horizontal way, but from now on, we will be writing that vector as a nothing but a vertical stack of components from V1 to Vn. So this is our another way to express or writing, denoting this vector. So this is, we usually call this guy as a column vector. Well, I fully understand why they are calling this guy a column vector, because row usually means the horizontal way, but here I am writing everything in vertical manner. So this is why they call it a column vector. So this is column vector. So if you understand the column vector, which is not a big deal, then you can understand the column picture of the given system of linear equations. Well, suppose that I have, let me go back to my original example. This one. What was the solution? Oh, well, the solution was one, and 2. Well, I have, this given linear system of equation. Let me try to express the equation using a column vector. How? Uh, 2, 4, and -2 plus V scalar multiple of 1, -6, and 7 plus W of 1. Even if there is no number here, but well, you can always consider as there is invisible 0 times W. So is right. 5, -2, and 9. Why this system can be translated to this one? Well, so if I scalar multiply this vector, this column vector by u, then this is nothing but every component should be multiplied by u, right? And every component must be multiplied by v, and every column multiplied by w. And if you add all these together, then first component is going to be precisely this one. The second component of this resulting vector, this one, and the last component is going to be that one. And here we are usually, so this is, well, this equality is nothing but comparing two three-dimensional vectors. So in order two vectors to be the same, then every component must be the same, right? So therefore, I claim that this expression is mathematically equivalent to this one. Okay, and this is what? Well, if you look at this expression, then the left-hand side of this equation, this vector equation, is nothing but the linear combination of 2, 4, -2, 1, -6, 7, and 1, 0, 2. So this is linear combinations of these vectors. So, and you must remember that the solution of this equation was 1, 1, 2. So what does it mean? So that means, if I multiply the first column vector by 1 and second column vector by 1 and last column vector by positive 2, then well, this is how you obtain this resulting vector using the linear combinations of these column vectors. So this is why the Professor Gilbert Strang is calling a column picture of the system of linear equation. Okay. Well, so since we are living in a world of Desmos, so let me try to visualize this. Yeah. So what was my first vector? Oh, sorry, I forgot. 2, 4, -2, 1, -6, 7, and 1, 0, 2. Okay, so the V1, let's see, V1 is a vector from originating from the origin, and 2, 4, 2. Not 2, -2, sorry. This is my first vector, and V2 is a vector from 1, -6, -6 and 7, and the V3 is a vector okay. All right. So, okay. Now I'm confused. Okay. So these are my three vectors. Okay. And what does it? The 1 times V1 plus 1 times V2 plus 2 times V3 is what? Oh, oops. Not right. Oh, okay. I should not be using this. Let's get rid of a bunch of ones. And something is not right. 고마워요. 네. So, so this one, this purple arrow represent this. Okay, and this is precisely the vector So as you can see here, so the purple vector exactly coincides to the red vector. Okay. Okay. All right. So this is the column picture. So, well, in other words, well, the row picture, in row picture, every equation can be translated to n-1 dimensional hyperplane. But in column picture, not a row, but the columns of these coefficients should be translated to a bunch of vectors. And well, after some, well, finding solution means being able to write down the right-hand side vector as a linear combinations of the column vectors on the left. Okay, all right. All right. Now, there are some singular cases. Well, I have changed the number a little bit. Suppose that I have this looking system of equations that has 3 unknowns and 3 equations. Well, and if you spend a little time on this question, then you can be easily convinced that there is no solution in this system. Okay. Why is that? Why I cannot find any solution? Well, there can be 2 explanations according to row picture and the column picture. Well, this guy has no solution because, well, according to row picture, each of these rows can be translated to a 2-dimensional plane in 3-dimensional Euclidean space, right? And having no solution means there is no common intersection point of these 3. Just like well, x plus y plus, so sorry, so I am using the xyz instead of ubw. The first line was this, and the second line was that, and the last one, 3x, y, 4z is 6. All right, okay. Well, can you see the picture? So can you see what is happening over there? So, well, there is, well, every 2 pair of planes, then you can find intersection lines, but there is no such a point that is contained in all these planes at the same time. So this is why, so this is my row picture explanation of why this system equation doesn't have any solution at all. Well, and according to the column picture, 1, 2, 3, V 101, 1, 3, 4. Well, in column picture, having no solution means that you can never be able to achieve this vector as a linear combinations of these three column vectors, right? So how do I geometrically interpret this scenario? That means, in other words, this vector, this column vector 2, 5, 6 is not an element of span of 1, 2, 3, 101, and 1, 3, 4. How that is possible? So I told you, usually, most likely, if you consider span of 3 vectors, then that must be, usually that should be the 3-dimensional space. And well, then in that case, if this guy is the 3-dimensional space itself, then this is the, well, clearly a member of 3-dimensional Euclidean space. Therefore, this guy must be the member of this span. But however, this one being not a member of this guy, this subset means this can never be a 3-dimensional space itself, right? The only possible explanation is the span. Well, even if I use 3 vectors for the generators of these spans, but this fails to achieve the 3-dimensional space. So this is only 2-dimensional space, and this guy is not a member of this space. So, well, just like this. Well, I have, let me say, well, this picture is not very accurate, but this is 1, 2, 3. And this is 101. And this last vector is, well, is actually a member, well, it contained in a 2-dimensional space spanned by these two. Right? Oh, by this, is it true? I don't know. Well, 1, 3, 4. And all these 3 vectors, these 3 vectors contained in one single 2-dimensional plane. And I guess this last vector, 2, 5, 6, must be somewhere around here. So this last, well, so if the last vector, 2, 5, 6, is not a member of, is not contained in this plane, then that means you cannot achieve this guy as a linear combinations of these 3. So this is the only possible explanation why there is no solution, according to the column picture. Okay. All right. So since this is the first day of the course, so okay, I will end a little bit earlier than expected. Okay. Thank you. 박수는 치지 마세요. 너무 부끄러워서.